This is lecture 23. Today we will be talking about intermolecular forces. That means the forces or attraction between different molecules. And there are 6 types of intermolecular forces or intermolecular interactions, and you'll need to be able to understand all of them and describe all of them in detail and use them to solve some problems. So we'll start with London dispersion forces. London dispersion forces, or temporary dipoles, are found in every single atom and molecule in existence. So every atom and molecule exhibits these London dispersion forces. And then we'll go through the list in order of increasing strength. So next would be dipole-induced dipole interactions, then dipole-dipole interactions, hydrogen bonding, which is something I'll introduce you to today. Then we have ion dipole interactions, and then finally ion-ion or ionic bonding. And so these are all intermolecular interactions, right? So between two atoms or molecules. So covalent bonding, you'll see, is not on this list. That's because covalent bonding is what defines essentially something as being a molecule. Now, the key to all of these is just going to be electrostatic interactions. So basically, it's just the positive regions of one molecule are going to be attracted to the negative regions of another. And the more positive or negative charge or partial positivity or partial negativity you have, the stronger those interactions are going to be. All right, so let's start now with London dispersion forces. So London dispersion forces, like I said, are the weakest interactions, but they happen among all atoms and molecules. So what these London dispersion forces are where they're derived is from the fact that the positive charge inside one atom can still see past its own electrons and see the electrons in another atom, right? It's not a very strong sight. You know, the positivity in one atom, the nucleus of one atom isn't strongly attracted to the electrons in another atom. But atoms can actually do something called dispersion, where they will move their electrons, or at least partially move them to one side. So we're talking about, instead of having 100% distribution over the whole atom, or in other words, 50% on the left, 50% on the right, we might change that to be 51% on the left, 49% on the right. So it'll have a slight shift, very, very slight partial positive, partial negative charge. So it's a little exaggerated here, but that slight shift of electrons is enough to get two atoms to have some desire to be around each other. And of course, these atoms are still bouncing around and so forth. So this might be a passing experience. And so we generally refer to these as temporary dipoles. So as two atoms or molecules move past each other, they might rearrange their electrons to get a better view of the other atom's electrons, right? A lot of good cheating jokes there. But the ability of an atom to move its electrons, so this rearrangement in real time of its electrons can be difficult. And so we measure that difficulty in what's called polarizability. So in other words, a higher polarizability means that the atom or molecule is more able to rearrange its electrons. It's more able to make itself polar, or at least momentarily polar, so that it can see another atom. Before I leave this slide, I'll just point out that here's a picture of Fritz London, the guy that came up with these London dispersion forces, or first described them, using a straw from a very tiny cup. All right, so let's talk about different things about molecules, how they affect London dispersion forces. So the first thing you want to know is larger atoms and molecules are more polarizable than smaller ones. The basic idea is they have more electrons that they can shift around. So in atoms specifically, they have a bigger cloud. So the farther the electrons out, the less they really care about what's going on in the nucleus. So it's a little easier for them to shift around. And that's reflected actually in the boiling point of different species. So here I have listed our noble gases, starting with helium and working our way down. And what you'll notice is helium has a super low boiling point. Its boiling point is at 4 Kelvin. Helium does not want to be a liquid. It's actually really hard to make it a solid because its melting point, I believe, is below 1 Kelvin. But so helium has a boiling point right at 0. But if you go to neon, its boiling point goes up a bit. And as we go down the periodic table, you'll notice these boiling points of these gases get higher and higher. So what's causing that? Well, as these get bigger and bigger, they get more and more polarizable, and so they like to stick to each other more. Sticking to each other is basically what liquids do. So as the intermolecular interactions increase, they like to stick better. That raises our boiling point. This can also be seen really easily with the halogen gases. So these come in pairs, right? So you have F2, Cl2, Br2, I2, and antimony 2. So these molecules always have 2 halogens in them. And you'll notice as we go from the fluorine gas, which has a molecular mass of 38 grams per mole, this has a boiling point of 85 degrees Kelvin. So this is way below room temperature, right? Room temperature is at 298 Kelvin. Cl2 is also has a boiling point a bit below room temperature, but bromine and iodine and this antimony gas, or antimony 2, all have boiling points that are above room temperature because as they get bigger, their intermolecular interactions are getting stronger. They're able to stick to one another more easily. So that is why Br2 and I2 are liquids at room temperature, whereas the other halogens, F2 and Cl2, are gases. All right, so size affects the amount of London dispersion forces you get. Shape is actually also going to play an important role, right? Because the idea here is you have to have the 2 atoms or molecules touching each other. So if you have a flat molecule, it's going to have a lot more surface area to interact with another molecule. So it's got more locations to have these dispersions. Whereas if you have clumpy ones, you're going to decrease your interactions. This can be seen very well in isomers. So here I have pentane and 2 of its isomers. So these are just constitutional isomers where we introduce some branching in here. And you'll notice for pentane, which is just this 5-carbon chain, it has a boiling point of 309 Kelvin. But if we start rearranging these carbons, and instead of having a linear 5-carbon chain, if we have, for example, 2-methylbutane, which has a 4-carbon chain with a branch, the boiling point drops slightly. So it goes from 309 to 301. And if we have 2 branch points to where we kind of have this tetrahedral geometry around the central carbon, the boiling point goes down even more to 282 Kelvin, right? So with a small molecule like this, where we've only got 5 carbons, this small branching might make a slight effect. If you have a much bigger atom, basically these dispersion forces kind of stack on top of each other. So let's say you had C12H26. This is a long 12-carbon chain. If that comes up to another C12 chain, those can lay on top of each other, and all of a sudden you have a lot of small interactions adding up to get you a very strong interaction. So even though London dispersion forces are the weakest interaction, if you have enough of them in a molecule, this can cause 2 molecules to stick together very strongly. All right, so that's London dispersion forces. Now let's go on to the next interaction, which is dipole-induced dipole. So this induced dipole, you'll remember we called the London dispersion forces temporary dipoles. This is another way of saying it. So the second interaction is a dipole essentially interacting with any other molecule. So a dipole, right, is found in polar molecules where you have a partially positive side, a partially negative side, right? In water, we have more electron density on oxygen, we have less on the hydrogens, so we got a partial negative on the oxygens. Now, if this water approaches something like O2, which is a nonpolar molecule, what it can actually do is induce O2 to move its electron density away from the negative part of water. Therefore, we have this partial positive, or this induced partial positive, in our nonpolar molecule. And now, as you can imagine, we have some negativity built up over here. So if another water molecule came in, its partial positive could see this partial negative. And this water could even come in at the O2 backwards, where the partial positive comes in. And in that case, if the partial positive is interacting with the neutral molecule, the partial positive is going to attract the electrons from the other molecule. So this is what we call a dipole, induced dipole interaction. It's our second weakest interaction. A stronger interaction, as you can probably imagine, is if we have one of these dipoles interacting with another dipole. So dipole-dipole interactions, this is number 3 on our list. So it's the third weakest, or it's another way of saying that is it's right in the middle in terms of strength. So here, right, we would have just a molecule with a partial negative and a partial positive, and the partial positive from one molecule will see the partial negative from the other molecule, and the partial positive from this molecule might see partial negatives from other things. Right, so the positive and negative ends are attracted, but of course the positive and positive ends are going to repel each other, and the negative and negative ends are going to repel each other. Right, so an example molecule here would be HCl. HCl has a polar bond, so the hydrogen is going to have a partial positive, the chlorine is going to be partially negative, and so these are going to be attracted to each other. But let's say then we have this liquid here where we have a bunch of these molecules around. So that's shown here in this diagram or picture. If we look at this central molecule right here, it's got this partial positive, and this can be interacting with the partial negative on this molecule. It can also be interacting with the partial negative here, the partial negative here, partial negative over here. So it's going to have a stronger attraction to molecules that are closest to it. But the idea is that it's not an exclusive relationship, right? This guy is going to be attracted to anything it can see that has a partial negative. Similarly, the partial negative is going to be attracted to everything with partial positive. Now, in our gases and liquids and even our solids, you have motion of your molecules, right? So if you're in a liquid, your molecules are all still kind of bouncing around each other. And so you're going to be constantly breaking and reforming these dipole-dipole interactions. And so often it is possible for you to get, for example, a partial positive facing a partial positive, but that's not going to be favorable. And so those molecules are going to try and move away from each other to eliminate that interaction. And of course, dipole-dipole interactions, like I say, are going to be stronger than dispersion forces, especially for molecules of similar molecular weight. So right here, I have methylpropane. So this is just a 3-carbon chain with 1 carbon sticking up top. And I'm comparing that to 2-propanone, also known as acetone. So this is also a 3-carbon chain, but it's got an oxygen sticking up, it's double bonded to that central carbon. So both of these molecules have molecular weights of about 58 grams per mole. But you'll notice for acetone, its boiling point is 329 Kelvin, whereas the boiling point for methylpropanone is 261. And so the 2-propanone or acetone has a much higher boiling point because it has this polar bond in it, and that polar bond can then have dipole-dipole interactions with other acetone. Whereas with methylpropane, you're just going to get these dispersion forces. We can see this in 2 other example molecules. So Br2 would have 2 bromines, right? And this would be a non-polar bond. So Br2 has a molecular weight of 160 grams per mole and a boiling point of 59 degrees Celsius. ICl, which would be the diatomic molecule between iodine and chlorine. This is actually a slightly more polar bond because chlorine is going to have a higher electronegative than iodine. And so this will actually have a very similar weight to Br2. So ICl has a molecular weight of 162, but its boiling point is now much higher because you have this dipole in ICl, this ICl bond. So that dipole is going to allow you to stick to other molecules. So 4th in our list after dipole-dipole interactions is actually another dipole interaction. but we give it its own class because it's especially strong. And this type of dipole interaction is what we call hydrogen bonding, or hydrogen bonds. So this, like I say, is the strongest dipole-dipole interaction. And to have it, what you have to have is a hydrogen covalently bound to nitrogen, oxygen, or fluorine. Why those three molecules specifically? Well, these atoms specifically, these three atoms have the highest electronegativity. They have very high electronegativity. So much so that when you attach a hydrogen to them, they pull most of the electron density away from the hydrogen. And it's actually not hard for these atoms to release a hydrogen while stripping away all its electrons. So just taking a hydrogen atom, ripping off all its electrons, and that's just a proton that flies off. And so what's going to happen then, though, in hydrogen bonding is the hydrogen will stay on these atoms or on these molecules, but it'll have this strong partial positive on the hydrogen. That hydrogen can then look at other partial negative groups and be attracted to them. Right? So the idea again, the electronegativity on nitrogen, oxygen, or fluorine makes hydrogen very partially positive. So much so that you almost have a formal positive charge on the hydrogen. And the small size of nitrogen, oxygen, and fluorine allow for the hydrogen to get really close to them. Why that is important is because then you can have this partially positive hydrogen on one molecule getting really close to the partial negative on another, and those are going to get really bound together. Some common examples of where hydrogen bonding occurs is, for example, in water. Water has this central oxygen and two hydrogens. Those hydrogens are very partially positive. You have this huge partial negative on oxygen. So oxygen sticks to itself a lot. So water actually has a relatively high boiling point compared to similar or other liquids of similar mass. And water can actually hydrogen bond to the oxygen in acetone, right? Acetone, again, is this 3-carbon chain with an oxygen double bonded in the center. And so this oxygen is going to have a strong partial negative. It's not going to have a hydrogen on it. So acetone can't hydrogen bond to anything else, but water can come in and hydrogen bond to acetone. Right, so it's something that can be done to acetone. It's not something acetone can do to other things. Another example is in methanol. So methanol consists of a single carbon singly bound to an oxygen, which is also singly bound to a hydrogen. So this oxygen-hydrogen bond is going to be strongly polar, and so you're going to get hydrogen bonding throughout this network. So methanol is generally a liquid, and you can generally have, so then you have this huge series of hydrogen bonding, this hydrogen bonding network running through most of the liquid. Let's see how you're doing with this hydrogen bonding idea, and I want you to tell me now which liquid on this list may exhibit hydrogen bonding. Go ahead and pause the video and try to figure it out. All right, so the rule for hydrogen bonding is hydrogen has to be bound to oxygen, nitrogen, or fluorine. The only molecule in here that has oxygen, nitrogen, or fluorine is this HF molecule. So HF is going to be hydrogen bonding, and fluorine is actually our most electronegative element. So this is going to have a very strong hydrogen bond system in HF liquid. Okay, so that's hydrogen bonding, but these partial negatives, partial positives can actually also interact with ions. So for this, we're going to call this ion dipole interaction. So in ion dipole interactions, we don't distinguish between regular dipoles and hydrogen bond dipoles. So we just lump them all into this category of ion dipole interactions. So what's going on here? So for example, if you have a salt dissolved in a liquid, and that liquid has a dipole nature, then the negative parts of your liquid can surround the positive cation from your salt, whereas the positive parts of your liquid can surround the anion of your salt, the negatively charged species, right? So water has partially positive parts, partially negative parts. That's why it's actually so good at dissolving salts, is because it can get salts into these networks like this. So the strength of your ion dipole interaction is going to largely depend on your ion. So for a doubly charged ion like magnesium 2+, you're going to have really strong ion dipole interactions, whereas with things like sodium plus interacting with water, you're only going to get dipole interactions of 405 kilojoules per mole. Right, so the charge matters. You'll notice that the strength of this bond between magnesium 2+ and water is a little over 4, and it's nearly 5 times bigger than the sodium because it's got double the charge. And if we've got double the charge, we've got about 4 times the strength. Compare that, though, to sodium interacting with water and cesium interacting with water. You'll notice that cesium is nearly, or is almost half of the strength as the sodium-water interaction, just because sodium is so much bigger. So bigger ions have lower ion dipole interaction strengths. Smaller ions have stronger interactions, and the more charge you have on an ion, the stronger these ion dipole interactions are going to be as well. And of course, the strength also depends on what your solvent is, what your dipole species is, right? So if I had methanol, you'd have a different strength here than with water, etc. So a really common place that we see these ion dipole interactions is in the ocean, also in your blood, in all your cells. All the water in your body is super salty. But if we think of just salt water, so the main component of salt water is water. And the second main component is sodium chloride. So sodium chloride, right, is made of sodium plus and chlorine minus. You put sodium chloride into the water will surround the different ions. So it'll surround the positively charged sodium ion, and it'll give all its oxygen, or it'll face all its oxygens towards that sodium ion. And so it'll solvate it. And then water will also surround the negatively charged chlorine ion with all its hydrogens, which have this partial positive ion. So what we get here is what's called a sphere of hydration. Specifically, if it's in water, we get this sphere of hydration. Here it's drawn in another way, where the water is in a three-dimensional structure around the ion. If it's anything else, like if we dissolve this in methanol, then we'd call it a sphere of solvation. If we dissolved it in acetone, it'd be a sphere of solvation. And so really what determines how well a salt can dissolve in a liquid is how well that liquid can accommodate the charge, how well it can hydrate or solvate that charge. So species without a dipole are not very good at dissolving salts. So things like hexane, which is just 6 carbons, very bad at dissolving salts, because hexane, it's not actually just 6 carbons, but it's C6H14. It's got no dipoles or anything, so it can have these London dispersion interactions with a salt, but that's it. Those aren't very strong. All right, last interaction we'll talk about is ion-ion interaction. So, of course, this is just the interactions between two ions. We've talked a lot about these types of interactions. So a great example would be sodium chloride still. You just have a positively charged species interacting with a negatively charged species. They're just attracted and they're going to stick together. So these are by far the strongest intermolecular forces, and these often have similar energies as covalent bonds. So ion-ion interactions can actually be as strong and sometimes stronger than molecules. Because we have these really strong interactions, you actually get really high boiling points and even really high melting points. So for example, if we look at the melting point of sodium iodide, this has a melting point of 660 degrees Celsius. Sodium chloride, which is table salt, doesn't melt until you get it up to 800 degrees Celsius, which most stovetops can't achieve these temperatures, so don't try melting this at home. Another great salt, magnesium oxide, this has a melting point all the way up near 3,000 degrees Celsius. So the surface of the sun is about 5,000 to 6,000 degrees Celsius. So you throw this into the sun, it'll start to melt. Some other salts that are very common are calcium carbonate. So calcium carbonate is the main component of chalk. a picture of it here coming out of a hot spring. So the reason calcium carbonate dissolves so well in water is not because the water is hot or anything like that, but because water can hydrate the positively charged calcium and negatively charged carbonate in here, right? Same is true for Na2CaO3. So this is sodium carbonate. So neutralize acids much better than baking soda. And you'll notice this has a rigid this has this interesting three-dimensional structure, and calcium carbonate does as well. These have repeating structures where the molecules find the easiest way to lay on top of each other, right? And so for polyatomic species like these, the way that the atoms and molecules lay on top of each other actually determines three-dimensional shape. So if you can have something that's really repetitive and really structured, like in copper sulfate pentahydrate here, then you can actually get three-dimensional crystals with predetermined shapes. So the shapes of crystals then is determined by the packing at the molecular level. The more regular that packing, the more likely you are to have this big three-dimensional structure. If you haven't seen it yet, over in the Eyring Science Center, there's a really cool display where they've got a bunch of crystals, some very large ones, made from different combinations of metals and polyatomic ions. Really pretty if you ever get the chance to get over there. What am I saying? You all have the chance to get over there. It's just one building. All right, anyways. Now that we've gone through now all of our intermolecular interactions, let's now work on comparing. All right, so dispersion forces or London dispersion forces, you'll actually also hear this called van der Waals interactions. But in these interactions, you have molecules just kind of trying to rearrange their electrons to be more attractive to one another. These types of forces usually are on the order of about a kilojoule per mole. So if you have a really long carbon chain, you can get up to as high as about 15 kilojoules per mole, right? So you have a big molecule, you can have a lot of these little interactions adding up. Next come dipole-induced dipole interactions, and these range in strength from about 1 to 5 kilojoules per mole. So on the low end, they're about as strong as a dispersion force. On the high end, they're about 5 times stronger. You then have dipole-dipole interactions, which range between about 5 and 20 kilojoules per mole. And by this range, of course, I mean different molecules are going to have different dipole-dipole interaction strengths. So this isn't saying that, like in this molecule, this dipole strength would range from 5 to 20. Each of these interactions does have a set energy, but that energy is going to depend on which molecule you're in. And you'll notice that with these dispersion forces, if you have a big enough molecule, you can actually get strengths that are rivaling your dipole-dipole interactions. What above dipole-dipole interactions is our hydrogen bonding. Hydrogen bonds can range in strength from about 30 to 150 kilojoules per mole. So now these are much stronger than these dispersion forces. They're significantly stronger than the dipole-dipole interactions. And above hydrogen bonding are ion dipole interactions, like what you get when you dissolve a salt in water. And these have interactions that are usually above 150 kilojoules per mole. And we compare all of these to ion-ion interactions or ionic bonding or covalent bonds. Those ionic bonding and covalent bonding usually have bond strength of about 400 to 1,000 kilojoules per mole, so you have to put a lot of energy into breaking them. So these intermolecular interactions are a lot lower in strength than ion interactions or covalent bonding, but they have a strength that makes real noticeable impacts on their macroscopic properties, such as melting point, boiling point, etc. And the key here is these are all electrostatic interactions, right? The more positive charge and more negative charge you have in a molecule, the more that's going to interact with another molecule. So how do you compare intermolecular forces? So if I gave you two molecules and said, how do you tell which one's stronger? Well, you're going to start by drawing Lewis structures, right? That's what we generally do with everything. So you'll draw the Lewis structure, find the molecular shape. You're going to want to be able to understand the geometry of this thing, right? Then you're going to determine if there are any polar bonds, if there's any partial charges on this molecule, or any formal charges, like what you'd get in an ion. And then once you have your structure, you know your geometry and so forth, your polarity, you're going to determine what intermolecular forces are present here. I'm going to compare their strengths. I'm going to say, you know, is it got a hydrogen bonding system going on? Is it all London dispersion forces, etc.? Then we're going to think about these intermolecular forces and how they're going to affect our macroscopic properties. Okay, we'll finish this off today with an eye-clicker quiz. I'll just ask you, what is the dominant type of intermolecular force in pure acetone? So this is 2-propanone. Its formula is CH3COCH3. Go ahead and draw out that structure and figure out this answer. Go ahead and pause your video. All right, if you drew out your structure, you should have gotten something like this. A 3-carbon chain where the central carbon is double bonded to this oxygen. Now in this molecule, do we have London dispersion forces? The answer is yes. We are always going to have London dispersion forces. However, the question is, what is the dominant type of intermolecular force? In other words, what is the strongest type of intermolecular force this molecule is going to experience? And it's got this carbon-oxygen bond here, which is going to give a partial negative to oxygen, partial positive to the carbon. So we would say that the dominant interaction in acetone, in a container full of acetone, is dipole-dipole interactions. Now, could this dipole interact with a hydrogen bond? Well, a hydrogen bond could come and a hydrogen bond with this oxygen, right? But this oxygen can't hydrogen bond to something else. Could we have dipole-induced dipole interactions? Yes, but that's always going to be weaker than dipole-dipole interactions. And could we have ionic bonding? No, we couldn't have ionic bonding because this isn't an ion. But we could have ion-dipole interactions. So if you can dissolve salts, for example, in acetone. All right, that is it for intermolecular interactions. And let me know if you have any questions.